All right, let's begin. So, thanks for that on the other side of the chance to do the warm-up, but there it is. I will eventually check your warm-ups at the end of the quarter, so toward the end of the quarter. We'll have all of those in there. Hopefully everyone's gotten a blue sheet that introduces the book homework for our unit. We have some worksheets along the way too, so this is not the comprehensive list of the homeworks. But this gives you at least the first few book homeworks, including tonight's homework that should be what's up there. Yeah, homework 1. Okay, so homework 1 is what our homework is for tonight. Sorry, I didn't write it up here yet. And it's in the book, so that's what will be checked tomorrow. Yes. That was Unit 1 quiz, yeah. We didn't have a test per se, but yeah, we called that the Unit 1. Yeah, so this is, we're already done with Unit 1. Look at that. Okay. Anything you want to say about Bhavesh's work here? I mean, this isn't meant to be crazy, but okay. That'll come back later. That expression is of interest to us for sure. It's not just random, so, but not today. Okay, so we're introducing a unit, like it says at the top of the blue sheet, on limits and continuity. And the thing that we're attempting to show here with these pool noodles, by the way, these are your other BC calculus teachers besides me, is what, of course? Yeah, a discontinuity, right? We've got a discontinuity, and Mr. Davis thinks everything is okay, but we're not so sure. Okay. Come on, it's cute, okay. We're actually, this will have just a culminating quiz. It's a pretty short unit, maybe about 2 weeks is about how long this lasts, and that's it. I mean, really a week and a half. We don't have too much to say, except to say something about limits and continuity, of course, as well. But we want to actually come out and maybe formalize the notion of limit a little more than you have in the past. I think a limit is an idea you had before in your previous courses, but we want to say more about it today. So this expression is one that that's going to be the subject of much focus and conversation. And we want to make sure that we understand each part of this. I think, like I said, I think you should have even been using that in your function libraries that you just handed in. Though I think the only limits you needed to use there were ones where the C was infinity or negative infinity. And we'll do some of those too. But we also want to think about a limit. We want to think about limits in the context of C values that are not infinity or negative infinity, just as we get close to some number. Could be 2 or something, right? So we want to think of that symbol as inviting us to let x take on values close to C, whatever C might be. F of x is, of course, the function itself. And we want to think of this as being almost like the limit as being kind of a function of the function, right? The function itself gets close to some number L. Keep in mind that the C value that we have up here is something that we're letting x get close to. And L is the thing we're claiming, if we're making the claim, that we're claiming that y is getting close to. Yes? Is that clear? Hopefully that's clear. That's certainly true for the end behavior limits too, right? We let x go to this thing, and we ask, what does y get close to? And the answer is maybe L, whatever L might be. So there's some annotation on top of those symbols that you've maybe seen before. And again, the way you might read that out loud is the limit as x approaches C of f of x equals L. We didn't leave anyone behind yet, have we? Interject whenever you like. Now, if I were to just ask you, what does it mean to approach a value? The thing we're going to look at in a second here is we're going to look at approaching some value at some x value C. Like I said, it could be x equals 2 or something. And the question is, what happens to y as we get close to that value? We want to hone in on that y value, whatever it is. L, we're calling it here. This is the definition that I copied directly from the book, so if you don't want to write it down, you're forgiven. And in fact, it's never something AP will test you on or we will test you on, okay? But I do want you to have seen it, and I want you to at least attempt to understand it for the good of, your mathematical heart. I don't know how you want to say this. Okay. This is the definition of a limit, and no one's ever shared this with you until now. Okay. So it's a little bit cumbersome to get into because of the symbols, but I'll be your guide. So assume f is defined in a neighborhood C, and by neighborhood we mean an open interval containing C. Right? So assume that f is defined. Now it doesn't actually have to be defined at C. It has to just be defined in the neighborhood around C. That could be punctured. And let C and L be real numbers. Then we say that f has the limit L if, and this is all these are tricky, given any positive number epsilon, there exists a positive number delta, that's a lowercase Greek delta, this is an epsilon, such that this holds. Such that this implication holds. So here, let me give you intuition, and then we'll return to the symbols. If I claim that as I get closer, and I'll show you the picture. Maybe I should show you the picture first. I'll draw this again here. If I claim that the limit as x approaches C is some number L, then what you should be, as the skeptic, you should be like super critical of me. You should be like, okay, really? Well, then show me that there is a delta that gets you within 0.005 of your limit L. Shouldn't there be, if you claim that's the limit, shouldn't there be some delta around C, that is to the left and to the right of C, that if we're inside of that you always are within 0.005, or whatever you want to claim the tolerance is, around this point? And if you can do that for every epsilon someone comes to you with, okay, I found a delta that gets me always inside the epsilon strip around L that you demanded. But then you bring me an even tighter epsilon. You're like, okay, great. Now I need you to find me a delta that puts me inside 0.0000005 of L, your limit. And if you can do that for every epsilon, that is to say right here, for every epsilon that someone brings you, there exists a delta such that we stay inside of that little strip, however thin it might be, then the limit, we say the limit is L. Fine, we can actually say that. And so that's what this says here. This is the piece that says that x minus c, what is this in absolute values? I might read that as the distance that x and c are away from each other is less than delta. So this is like the tolerance of the input is delta. If that implies that we're always only epsilon or less away from L, the function, the distance between the function and L is epsilon and no more than epsilon, then we can write this. I have a slightly more polished picture here. I'll take you back to it in a second. So like I said, you come to me with a tolerance that you're gonna name, and then I'm gonna have to provide a delta for any given epsilon that you might bring me. I need to be ready to give you a delta that gets me close to that point. And I think it's worth doing. I'll put the definition up here again, but I think it might even be worth doing an example of that here. So we'll do that in a second, maybe too. Even though, like I said, AP and we will never test you on, I think it's worthwhile to say what we mean by this. The two things I underlined that couldn't be more important, I feel like. For any epsilon, there exists a delta, is like kind of the critical piece. Such that if you're within delta, then you're within epsilon. If x is within delta away from c, then f is within epsilon of L, right? That's the thing we're looking for. Does that make sense? Have I demystified the symbols a little bit? I hope. I don't know. But of course, you need to be ready for someone to come to you with any epsilon at all, right? It's not just like we can assume epsilon is 0.01 or something. So it's actually a little bit tricky to establish even some of the simplest limits. keep in mind that, like I said, we're in this punctured neighborhood of C. The actual value at the point, the actual function value at that value doesn't matter at all for this, right? We're in the neighborhood around it. So let's use the simplest example I can think of, a line. So you know enough about this graph and the behavior of this function as a nice long continuous function with domain all reals that I think you already understand what we mean by this. What is the limit when we evaluate this? Obviously it's, what does y tend toward as x tends toward 3? 7, right? I think that, I think because of what we know about this function, we can be a little cavalier here. But I just want to be able to tell you right now, though, that even if that wasn't true, even if the function didn't evaluate to 3 there, evaluate to 7, maybe it was undefined there, we still have this notion, the thing we're plugging in here is not ever 3, even though it felt like we just plugged in 3, I promise. I mean, we're not actually going to be doing this right here. We're kind of thinking that we did. The thing I want you to be thinking that we just did was we just plugged in 2.9, 2.999999, or 3.00001. What, as you get close to C, or 3 in this case, what does y approach? And the answers you'll get are like 6.99999 and 7.00001. Yes, you can try it on your calculator. You can plug in those two things. And it doesn't matter in answering those questions what the actual value is. This is like a little bit of a broken analogy, but we'll go with it. Okay, so here we got two trains coming at the value from the left and the right. And of course, what happens? That's right, they crash. And the question is, of course, what y value do they crash at? And the answer is 7, and we're done. We're going home. But if we have one that's more well, we'll do one with the, right, there you go. Doesn't matter. The big trains, if there's like a tiny hole in the track, there isn't here. But if there is, it doesn't matter, they still crash. Let me show you one that's, and those are train crashing videos if you want to click on them in your own time. Okay, we don't have time to click on them right now, but here you go. It is pretty exciting, but here's a function that's very similar. In fact, what's the only difference? Right. What is the limit as x approaches 3 of this very similar function? Yeah, now we have this graph instead, and it is still 7, but you're like, I demand to see the trains crash. Will the trains crash? Yeah, I mean, the fact that there's a little tiny pin-sized hole in the track means that it doesn't matter. They'll crash either way. What is f of 3? 0. Will the trains crash? Yes. I know this is non-technical. So what's the limit there, though? The limit is still 7, right? So I just want to, we're going out of our way to construct this kind of strange function, just to show you that the limit is still 7. Again, it doesn't depend on the value. The value of the function is 0, neat. Like, who cares, right? It's the behavior around. We're never plugging in 3. We're plugging in 2.999 or 3.0001. And if you plug in those values into this function, you will always get something close, ever closer to 7. Do you agree? Yeah, I think so. It's 7, right? Let me actually take this opportunity. I think I can do this here. To maybe, yeah, I think we can do it. To maybe try and go back to that definition just to show you how it connects to what we're just now doing. Because the trains is not super satisfying to me. I want to make sure you're okay with like establishing this limit using the epsilons and deltas. So maybe just like by feel, for this equation right here, 2x plus 1, if we claim the limit is 7, if someone came to me with an epsilon, what do I need to show? I need to show that 0 is less than x minus 3 in absolute value is less than some delta. And I need to show that that implies somehow that f of x minus 7 is in absolute value less than epsilon, right? So in practice, the way this works is like someone would come to me maybe with an epsilon, and I would be like, I would 0.001, and I would have to show that I can come up with a delta that keeps us within your epsilon of 7 for this function. Now actually, we know what f of x is here. It's 2x plus 1. So that would be us trying to get this to happen. And actually, we can go further with this. I say that this is, we can factor out the 2 here, that this is what this says too. Maybe divide by 2. In fact, that actually gives me something to say over here maybe. What do you think you might want to let our delta be? If someone comes to me with an epsilon at 0.001, what do you think you want to let your delta be in order to stay inside of 0.001 of this? Or let's say it's only 0.5. How about that? Something. So this is plus 0.5 and this is minus 0.5, above and below 7. So they want you to come up with values, a tolerance around 3 that keeps us between 6.5 and 7.5 for the y value. You with me on this? They came to me with an epsilon of 0.5. What do you think our delta we should choose? What neighborhood, what size should we choose to make sure that happens? Think about this line and what it looks like and its slope in particular, and maybe some of this algebra I just did. What this reveals is that no one understands what that's cool. It's all good though. Okay. So can you picture this here? What do I have to stay in between here? Minus what and plus what? You see it? You want to take a stab? Yeah, in this particular case, it'd be minus 0.25 away. So I claim that you need to be between, or what you're saying, is between 2.75 and 3.25. And then that will keep you between 6.5 and 7.5 for y, yes? For this particular example. So minus 0.25 and plus 0.25 to the left and right of 3, right? So I say let delta be. Now I'm actually going to erase this work. Okay? I say let delta be any, and this is the thing, you need to come up with a delta that's like a function of the epsilon that someone gives you, right? Just like we've just done. He didn't say just 0.25. He said take whatever epsilon is and divide by 2. That gives us like a formula. If that's always what we do, then what we've done is not just for any one given epsilon. We're about to do this for every epsilon. And that's what's demanded by the definition of a limit, isn't it? For every epsilon, there must exist a delta such that this happens. So you ready? If this is true, which we're allowed to say it's true, we can choose a delta of any size we like as the owners of this function. And I choose my delta to be whatever you come to me with an epsilon, I'm going to divide by 2. Okay, so what does that mean then? What's the consequence of this statement right here? If we demand that 0 is less than x minus 3 in absolute values is less than epsilon over 2. Well then, as a consequence, you'll see the same algebra just backwards now. You get this. Right? And that is, I mean, we can ignore the 0 if we like. This is just 2x plus 1 minus 7 is less than epsilon, and that's exactly what we wanted to show, right? We wanted to show that f of x minus L, in this case 7, is less than epsilon. Sorry, that's a little hard to read, but down there. Right, so what we've done is we've shown that no matter what epsilon someone brings me, I'm going to make delta be that thing divided by 2. And if I always make that choice, then we have this. That is, I'm always going to keep us within epsilon over 2, or delta, of 3. And if I make that choice always, then this is a consequence, this is a consequence, this is a consequence, and therefore, if this is the choice of delta, then it must be true that we are within epsilon of L. Is it clear how that went? This choice of delta implies that we're going to make it on epsilon. Yeah. From here to here? I just distributed the 2 in. It's positive, so we can do that. Is that cool? I mean, it's not critical that you understand this, but I want you to like at least have a feel for how these go. This is actually the very simplest you can do. If you try to do this with a quadratic, it becomes quickly really, 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 really messy because it doesn't. Well, we won't go into it, but this is the key, right? For any epsilon that you give me, I can choose a delta such that y is within your epsilon of L. I have a method for always doing that, no matter what. Sure as can be. Okay, sorry. Let's do another one. I digress. We'll go back to trains. I promise. Okay. You like the trains better? I just have to say it at least because we are in math class. Okay. All right. So here's a graph of x plus 2 squared minus 4. It's a parabola, of course. And we're asking what happens when we tend towards 0 for x. Well, it appears that, and you can plug it in too and play around with the values. Of course, what does the limit evaluate to here? What's f of 0? 0, good job. Yeah. What is, will the trains crash? Oh, we have to see 2 trains crash, of course. They do, and what y value do they crash at? Yes, is the answer. What y value do they crash at? 0, and in this case, yeah, there's not much to say. The limit is 0. Okay. Here's another problem. Sorry. Is that too fast? We're not doing anything too sophisticated here. I'm still drawing the train, Mr. Chase. Please don't go to the next slide yet. This one, again, is meant to look somewhat familiar. This should be a good caution to you. What happens if we plug in 0 here? Yeah, we can't plug in 0, right? 0 is undefined for this function. Yet, can we still maybe determine the limit? I think maybe we can. I don't know. Let's just take a little look at the algebra on this. Can you convince yourself that this is the graph we have? Wait, what? Do some algebra, please. Do some algebra. On the numerator, what do we get? I mean, this is just a rational function that you might have studied in pre-calculus. And what do we call x equals 0? What's going on there? 4x. What do we call x equals 0 for this graph? So what do we get? Yeah, x squared plus 4x over x, which has the same limiting behavior. By the way, notice that I have the limit on each one of these here. That has the same limiting behavior around 0 as x plus 4, which is why this picture looks the way it does, right? So it is a line with only one exception. It would be a mistake to say that this function, x plus 2 squared minus 4 over x, if that was like f of x, is equivalent to the function y equals x plus 4. Because they're a little different. How are they just a little different? Go ahead, Josh. Right. Then we have, and what did I say? What is that from our pre-calculus language? What property does this graph have? What feature? It has a hole. It has a removable discontinuity at x equals 0. Your calculator, if you graph this on your calculator, you probably won't see it, but if you go to the table, it'll say error, right? You try to graph this, and your calculator doesn't do this the favor of having like a open circle there for us. But you know, and I know what it should look like. Okay? So it is a little different, but it's certainly true that these equalities hold because we're talking here about the limiting behavior. So even though you can't plug in 0, this is why we want to caution you the whole time here. Even though you can't plug in 0, can we say what the limit is? Yeah. It's still the same as the last, as this line, right? What is f of 0? It's undefined. Will the trains crash? Of course we have to have, bring them in. Go ahead, there we go. Again, they don't mind, actually all. They're like racing at, 100 miles an hour. They don't mind that there's like a pinhole at the place where they're gonna crash. So it's really fine with them. They're gonna crash even so. And the question, of course, is at what y value are they gonna crash? Someone already said it. What is the limit here? 4, right? Do I have a thing that comes up here? Yeah. And again, let's just say it one more time and put it in a box. The value of f of x at c, irrelevant. The thing we care about is what happens as we get close to it, this function. If you plug in negative 0.001 or positive 0.001, what kind of y values do you get? And you'll always get 3.999 or 4.0001. Try it. You'll see. Questions so far? Okay, let's do some visual here. I don't have any functions for you. I just want you to evaluate the limits I've given you here. Go down the list here and just visually say what those are. Ready to do this? The first one's a little troublesome, isn't it? What do you want to say on that one? You want to take a stab, John?
I kind of want to say there isn't one.
Okay. Is that what you were going to say also? Or sorry, what's your name? Becca. Okay. You want to make a case, too, for the other? I don't know. Okay, yeah, maybe we could, and so in some senses you're both right, yeah. So is there an overall limit here? I would say no, it really doesn't make sense because we can't even approach it from the right. There like isn't a right train. But is there a sense in which there's a limit? Like, yeah, absolutely there is, and we're actually going to use that notation. I think I introduced it on the next slide, but we'll do it now. We'll say the limit as x approaches 3 from the left, we'll use this notation to mean from the negative area. Over here, from over this side, as you come from over here, you get what? What is the answer to that question? 3. But the overall limit is undefined because that requires both pieces, right? So we'll say more about that in a slide or so here. 2.5, what do you want to say there? Just say what you think it is. Yeah. 2.5. This is good to emphasize this. The trains don't need to come from very far away, okay? That's fine. We can, as long as we can plug in values, 2.4, 2.49999, and also 2.50001, right, on both sides if we can narrow in on it, okay? And then 2 is 2, good. Do you get it? I think you do, maybe, okay? It's not 1. There's certainly lots of things you don't need to write this down. I just wanted to emphasize that certainly you already know from an intuitive perspective, like lots of functions that that this will happen with, and ones that it won't happen with, right? So you've been studying those in your library of functions that you've made, and for the most part, for well-behaved functions that like we know and love, and you know well. You kind of, you have a feel already a little bit for when you could just plug a value in and see what the limit is, right? Like, do we have to be cautious if it's just a line? What if I just give you a straight up quadratic and I ask you, what's the limit as x goes to 4? I think you would just probably plug in 4, right? And to some extent, we're going to rely on your previous knowledge. Certainly, polynomials are always going to be safe. Just plug it in if you're evaluating the limit. But we do need to be careful about some of these other kinds of functions, right? Or evaluate the limit as x tends toward pi over 2 for secant x or something like that. Right? Be careful, right? You know that thing goes. If you're familiar with anything from trig, you need to be careful about certain rational functions. Certainly log functions. Absolute value functions for the sake of limits should be fine though, right? There's no discontinuity. Well, I don't know. Well, we need to think about how continuity and this idea fit together, don't we? There's obviously some kind of a connection. Here's a graph of, and you need to include this piece here, of the greatest integer function, which you don't really need to remember very much in life, but but here it is. It's really the time when it's most useful to us is when we're like discussing limits and continuity. Like, let's bust out the greatest integer function. So we have some discontinuities and some jumps to work with and fun limiting behavior. Just so you know what the greatest integer function looks like, let me clarify these a little bit. It's open on the right, closed on the left of each of these little segments. So it is a function in the proper sense. Okay. So what is the limit as x goes, and each of these jumps occurs at an integer, okay? Just in case you don't know what the scale is on this graph. So what's the limit as x tends toward 1.5? That is, when x gets close to 1.5, what does y get close to? Yep, you got it. What about 2? Yeah, again, we haven't really seen this happen today. I think only an example we've shown, in fact, are ones where the limit exists. So you would like to see the trains not crash, wouldn't you? There you go, no crash. Okay. As we come toward x equals 2, from the left and from the right, the two trains don't crash, right? Like, that's the problem. If the tracks are like, if there's like a little hole in the track, we're going to crash. But if the tracks are like wrenched like this, like they are here, then there isn't going to be a crash. We should think of that as being good, though, maybe. I don't know. It doesn't exist, right, or undefined. The limit doesn't exist. But now we can finally introduce this language of, by the way, the yellow and the blue train, the left and the right train. We can replace that with this more formal notation that we just introduced on the last slide. From the left, we can say, what's that? Yeah, 1. And from the right, 2, right? So you understand now what this means if you didn't before? From the left and from the right, okay? And we can explain why this is true, right? In general, we need these to agree. If these agree, then this will definitely be defined to be whatever they agree on, if they agree. So we have a little bit more of a technical way to talk about trains now, okay? 1.5 from the left, we can say that's 1. From the right, that's also 1, and so therefore the overall limit must be 1. The overall limit is only established if the left and right hand limits agree, right? So we can even put it in a black box. There we go. We can only say this if and only if we get the left and right hand limits agreeing on the value L, right? Or replace black box with like train diagrams, right? It's all the same, really. Okay. You do not need to write all these down, but if you would like, all the properties you'd probably expect to have happen about limits do happen, okay? So, for example, and I intentionally made these small enough that you can't like read or copy them, so that you won't copy them, okay? So, like for instance, the first one says the sum rule. The limit as x goes to c of f of x plus g of x, get this, is equal to L plus m, if L and m are the limits of f of x and g of x individually, right? Whoa, okay? And all the rest of them are equally not very exciting, right? They're all exactly how you would expect them. But I would encourage you just like glance at them and say to yourself, oh yeah, that kind of makes intuitive sense. They're on page 58 of your book. Can I show you one more that's going to blow our minds a little bit before we leave here? Okay. There is a proof of this in your book, but we're just going to kind of tell you what this limit is, and we're going to like run with it, okay? This is a graph of sine x over x on your calculator. First of all, if we're trying to evaluate the limit as x goes to 0, we should all acknowledge that that's like a little bit problematic, isn't it? Because you can't plug in 0. But it appears on the graph, and you're welcome to play around with your calculator and see this. If you plug in really close values, it seems to be getting closer to what? It definitely looks like 1. Yeah, and that is the answer. There is a more rigorous proof that's presented in your book, and you can look at that, or on the internet, wherever you like. And so we need to know that this is true, And that's something that AP cares about and we will care about. And I think there are a couple problems like this in the homework tonight. So all of these, for example, I think we're about out of time here, but all of these are ones we can solve with only that knowledge too.
Wait, so the size
Are we done? What's that? Yeah, what's this one gonna be? I mean, replace the 2x with a smiley face, right?
Can say, following, please come to the main office.
And we still have like a sign or something over that symbol. All right, more tomorrow. Bye. I'll miss you.